When we look at quantum physics, immediately the first concept that jars us, the first concept that comes about is this concept of wave of possibility, because that's what the equations of quantum physics, the mathematical equations, give us. Wave of possibility. Immediately the question comes, what is a wave of possibility? What does it mean? Well, it means, of course, in a very simplistic way, bundle of possibilities. But it's a specific bundle of possibility that behaves mathematically like a wave, and that has specific meanings. So let's get into that a little bit more specifically. Let's imagine that we have released an electron right in this room, in the center of this room. Waves have this wonderful characteristic that distinguishes them from objects that we call particles. In that they spread all over. This is a three-dimensional wave, so it will spread in all the directions. Just like imagine seeing water waves. Those are two-dimensional waves on the surface of water. Imagine that now we have the same kind of thing spreading out from a center, but doing it in three-dimensional space. So the electron now, very soon, can be all over the room because they move pretty fast. In a matter of moments, electron is all over the room because the wave has spread. What does that mean, though? Suppose an observer sets up a three-dimensional grid of Geiger counter. If we have these Geiger counters, will they all go tick, tick, tick and detect the electron everywhere? It just smeared out. An electron which was like concentrated at a point now is smeared out all over the room. Is that all it means? No, it doesn't mean that. This is where quantum objects are very mysterious. They're paradoxical, because when you observe them, we always find them localized in one place. Only one Geiger counter goes tick, and that's where we have found the electron in that particular experiment. How do we know that it was ever a wave of possibility? We know because if we do many such identical experiments, same object, identical object, electron, the electron will be found, all these other counters, in one experiment or another. If we collect all these experiments and plot them, where we found them, we plot that, and probability of finding them at that place, then they will look like a probability bell curve. These bell curves are quite well known. Probability curves usually look like this, and the electron then is just we say probability distribution. In many measurements, electron appears to be a probability distribution. So this is one way of interpreting the wave of possibility. Wave of possibility means possibility comes with probability. If we make many measurements, we can get the probability distribution of where the electron can be expected to be found in a particular measurement. So what happens to the wave-particle paradox? The paradox remains, though, because it was a wave and then it's becoming a particle. Electrons are both wave and particle. In fact, we have to qualify a little more. It's a transcendent wave and immanent particle. Wave of possibility in potentia that becomes a particle in the manifest world. And it's a paradoxical object. We just have to live with it. There is no way of asking the question, well, how can it be like that? It doesn't help. It is like that. Here is a wave, and waves become particles whenever we observe it. Of course, then we have the measurement paradox. But before we go into the measurement paradox, let's look into this in some more details, because maybe some other ways of getting out of this kind of question can be devised. The way to do it is an experiment called the double slit experiment. We allow the electron to pass through two slits at the same time, a double-slitted screen. So electron is passing through both slits, and imagine that you are holding behind the slit a photographic plate or a fluorescent screen. Either way, there's a measurement that is taking place, and we always measure a whole bunch of events together. What do we get? What we get is very, very interesting. We don't get electrons just collect behind one slit or the other slit, which would what we would have expected for Newtonian objects. If you throw baseballs and you have two doors fairly close by, and you throw baseballs, they will either pass through one door or you will pass through the other door. And you will collect them exactly like that behind the doors. You will find one bunch and then the other bunch. Instead, what we find is a whole bunch of places where the electrons show up. They are called the bright fringes. They are the places of the photographic plate or the fluorescent screen which will receive the electrons. And then in between there will be no much electrons. There will be nothing. Bright and dark fringes. And it turns out that this is exactly what happens when water waves pass through such a double slit. You get very similar patterns. And we understand it perfectly. If you look at the wave mathematics, you can work it out mathematically. You can also understand it by just simply drawing the waves and allowing them to interfere. What happens is that both waves are coming at various places of the fluorescent plate. And if you see a wave coming in a same phase as the other wave coming at one place, obviously the two waves add together. This is the special property of the quantum wave. Because they are waves, this is how we know that quantum objects are really waves. They add like this, they add algebraically. This is the way waves add. They interfere. We said that there is a phase relationship between the two waves which allow them to interfere. This is crucial. This is where we can say truly that they are not any old bundle of possibility. They are wave of possibility. Waves add like this. They can interfere. So what is happening? At some places they interfere in this constructive way. They add together. So we get more probability that the electrons will arrive in those places. And in between, one wave arrives with one phase, the other wave arrives on the opposite phase. And then they cancel each other out. There is no probability at all that any wave will arrive in those places. So we get alternative bright and dark fringes. But notice that wave is becoming a particle every time you're observing them. So notice the graininess of these images when you actually do the experiment with quantum objects. The fluorescent plate will always show distinct graininess of where the object is arriving. So whenever we are actually seeing an electron or a photon, it's arriving like a particle. So measurement paradox remains. We understand now the wave-particle duality. It's not a duality. Waves are becoming particle. We can verify that also very, very beautifully. Some people initially suggested maybe what we have is a property of the entire ensemble of objects. Maybe it's not a property of the individual electron, that it's a wave. Maybe only when we pass many, many electrons, then only we collect this interference pattern. But if you pass very weak source of, if you take a very weak source of electron, so weak that only one electron at a time passes the double-slitted screen, all you have to do is to wait. If you wait long enough to collect enough electrons, you find that no, still the distribution of fringes, that alternative bright and dark fringes, that pattern, interference pattern continues. So even when we are passing one electron at a time, the interference pattern still persists. What does that mean? That means that even a single electron really divides itself, becomes two waves, and the two waves interfere, therefore the interference pattern. When the electron is falling on the fluorescent plate or a photographic plate, it's not falling smeared. It's always falling at one place, and it's falling at classically forbidden places. Sometimes it falls classically allowed places, like right behind the slits. Other times it's falling at classically forbidden places. So it's giving away its wavy secret, even while it's being seen as a particle. Wavy secret, why? Because if it were a classical particle, Newtonian object, it could never fall in places other than right behind the slits. So these electrons really are very strange objects. They really are transcendent waves that become immanent particles when they collapse on the photographic plate or fluorescent screen. Now, of course, we already went through that measurement paradox. What is changing them? What is changing the electron from its waviness, from its possibility pattern to an actuality pattern? Agreed that the wave-particle paradox is not so hard to understand. It can be understood just by saying that, well, okay, quantum objects is just different. There's a both and kind of logic rather than either or kind of logic. In classical physics, we get either wave or particle. Here we get logic of complementarity. Electrons are both particle and wave. But remember, there is that huge difference. The waviness is always in a transcendent domain. The waviness always exists outside of space and time, in the domain of potential. In the immanent domain, as soon as you have collapsed it, it's always a particle. This too can be verified directly. What we can do is that we can set up things in such a way that whenever one electron passes the slits, we can try to measure which slit it passed through, because we are convinced that it must pass through one slit or the other. Suppose we try to measure the electron right when it's passing through one slit or the other. What happens? What we find is really quite interesting. What we find is that now the electron behaves like a particle. If we do this, then we always get like only two fringes right behind the slits. We don't get the interference pattern anymore. What is the explanation? Well, think about it. Where have we measured the electrons? We already have measured the electron while it is passing through. Remember, measurement changes possibility into actuality. So the electrons are already actual particles when they are passing through the slits, and therefore they cannot interfere anymore. They don't split and they don't interfere because they are already collapsed into particles. So in this way, all aspects of this wave particle remains intact. There is no other way of understanding them that will restore Newtonian physics, that either or kind of way of looking at things. There is no way to understand even both and in a simple way. Simple way of both and would have been that, okay, this is wave and particle both somehow. No, it's not like that either. It's a transcendent wave becoming an immanent particle. There is a transcendent domain of reality. There really are two different worlds of reality. We have to somehow reconcile that with our philosophy, with our worldview. We somehow have to understand that. What is also being suggested by non-locality? Where does this interconnection exist? The same thing is being suggested by discontinuity. Where does the electron go in between quantum leaps? Where it goes is to this transcendent world. Where it goes is it becomes a possibility wave. In between, what is it? It's not an object that we recognize as a particle. It's a wave of possibility. That's the only way to understand it. that there is a domain of potential and then there is a domain of actuality, the manifest world, the space-time world of Newtonian vintage. The space-time world for macroscopic objects, because of the large mass of macroscopic objects, appear a lot like Newtonian world. Because of large masses, it turns out Newtonian mathematics holds for the movement of these objects. They don't spread very fast. They are still waves, but they don't spread very fast. Suppose you ask the question of, okay, here is the desk that you are sitting at. And in between looking at the desk, you close your eyes. Will the desk be at the same place when you open your eyes? Quantum physics says that no, if the center of mass will have moved even in that split second during which you closed your eyes. But the movement will be so small, 10 to the minus 17 centimeters or so, that you cannot possibly see it with your naked eye. Can we measure such small distances? Yes, we can. Today, laser measurements give us such accurate measurements of position that people actually have measured macroscopic objects and verified that yes, the center of mass does move when they are allowed to spread without collapsing. Nobody is looking. Looking changes things. Looking collapses objects from possibility into actuality. Our looking, this mystery, what is in our looking? This mystery becomes a fundamental mystery. This mystery, if properly addressed, can change our worldview, can really change the way we think about things. So how should we think about things? Let's get into a little bit more detail. Let's look at how scientific materialists, this idea that everything is matter, how those philosophers look at things, look at the world. They theorize that matter has this micro-macro division. Micro makes up macro. So at the base level, it's all elementary particles. Matter consists of elementary bundles of matter, quantized matter, little objects that we call elementary particles. And then the idea is elementary particles make conglomerates called atoms. Atoms make bigger conglomerates called molecules. And it's still all quantum objects. This is still very micro. But then these molecules add together and they bring up the idea of the macro. They make bigger and bigger objects, and there is a transition, but you get macro objects pretty soon. Some of these macro objects have another strange phenomenon that takes place that we have known for a very long time, ever since human beings existed. They have always noticed that some things are living, some things are non-living. So somehow you have this micro matter building up what we call living cell. They're also building up things that we call non-living, like molecules can get together and build up a piece of rock. But then they also build this what we call living cell, and then conglomerates of living cells, and then ultimately we get this wonderful conglomerate of cells that we call a human being, brain of the human being. So this is the idea that scientific materialists give us. Elementary particles make atoms, atoms make molecules, molecules make living cells, some of them are neurons, neurons make brain. And then this brain makes consciousness. Materialists cannot make a huge thing about knowledge, knowing, and all that stuff. They can just say that, well, whatever we have, whatever we experience, it's just brain phenomenon, because there is nothing but material objects, remember? That's the basic philosophy. Therefore, whatever happens to what we call the human condition, at the human condition, we of course experience knowing, we experience thinking, we experience feeling, we experience sensing, we experience even something called intuition. But scientific materialism cannot say that any of those things are real things, quote unquote. Only matter is real, And therefore, there must be some sort of epiphenomenon, secondary phenomenon of the brain. Brain makes consciousness, brain makes the mind, brain makes our feelings, brain gives us intuitions if they existed. It's all brain phenomenon. So materialists concentrate on this 3-pound universe, that is, as it is sometimes called, the brain. Brain is responsible for all our phenomena. And ultimately the cause is all at the elementary particles. This is called the upward causation model. Upward causation model, upward causation because cause rises upward from the elementary particles to atoms, to molecules, to cells, to the brain, and to consciousness. So in this view, there is no such thing as free will. It's purely Newtonian view. Now we, of course, even in the introductory lecture, I talked about Heisenberg and his uncertainty principle. Where did that go? Well, according to this kind of view, what happens is that the uncertainty principle exists, and it exists in the submicroscopic level of objects like for elementary particles, atoms, and molecules. Certainly we cannot determine the trajectory. But remember, when we did the electron experiment of a possibility wave, we talked about these bell curves, probabilities, and those probabilities can be calculated. So long as there is a whole bunch of electrons, so long as there is a whole bunch of protons and neutrons that make up bulk matter, most of bulk matter, we do have the ability of predicting their position according to the bell curve. And as you know, probability becomes pretty close to actuality if you take large numbers. So majority of scientists today believe that some kind of statistical determinism can still be formulated. And we can go on living like as if Newtonian physics is correct at the macro level. That is the belief. The belief is all this stuff that is happening in the submicroscopic level just are a little irrelevant. Irrelevant because they don't bleed through and make their effects felt in the macro level of reality where we live. Is this true? We have to examine it. We have to examine it for each and every case. We have to take each of these principles and see if this is true. If the micro level principle really should bother us at the macro level. We should not be too hasty. The second thing is also very, very important. What these scientists often say is that the micro level, macro level arguments will produce often a little bit of puzzle at the macro level, but maybe we don't see those puzzling things at the macro level at all. For example, I mentioned before discontinuity. At the macro level, the effect of discontinuity is minuscule. I mean, after all, you are collapsing a table and a chair and so forth through our observation. Let's see that that is true, and there are discrete measurements indeed, but the differences of 10 to the minus 17 centimeters for all practical purposes can be ignored. So for all practical purposes, we can say continuity is regained back. Similarly, we talked about non-locality, and a space experiment has proven that indeed objects like two photons can communicate at a distance without having a signal between them. But suppose we just declared that, okay, this is fine. I mean, the world of submicroscopic objects is a little bit weird. This is called quantum weirdness. So we have some weirdness in that world. But what does it mean to our world? And they point out a very important thing. This is also true, that if you do an Aspe-like experiment, what does it take to tell that something very peculiar is happening? Think of the experiment. Here is a whole bunch of photons that is being realized, that is being released by, let's say, decay of a laser irradiated atoms. They are releasing 2 photons, again 2 photons, again 2 photons, a whole bunch of pairs of photons. And each pair of photons have that correlation, non-local correlation. So one part of the pair goes one way, the other part of the pair goes the other way, and 2 observers measure them. But suppose you are looking at this one pair and then another pair, then another pair, then another pair, and you are looking at all this data. So you look at one place, what do you see? You see random photons, that's the name of quantum of light, arriving at different places. You don't see any relationship between one photon and the next photon, because that's a different pair. Only when you look at this photon over here and that pair with which, that part of the pair with which it was correlated, you see that, there is a relationship between those two. How can that happen? Because there was no communication. And you'll see that, that is quantum non-locality, very strange. This photon communicated with that photon. But until you have seen the second set of data, you couldn't say anything just looking at the first set of data, you see. So these scientists make the very important point that information is not being transferred from one place to the other. Looking at this data, you could not infer anything about what is happening over there. And therefore the macro world is safe from this quantum weirdness. Why should we bother? If we cannot see quantum leaps in the macro world, if we cannot see quantum non-locality effects in the macro world, then why should we bother? This point is often made. So 2 points here. One is that the macro world approximate classical Newtonian physics holds. It's called correspondence principle. And so for the macro world, we can take Newton's physics and use that mathematics to get predictions and go on with our life as usual. And second of all this weird stuff of quantum physics like non-locality and discontinuity, if they remain in the submicroscopic world and never bother us at the macro world, then we don't need to worry. Then we are safe. This is the way that most physicists look at things.